Swayam Prabha. Digital India. Educated India.
We have been discussing analysis of two-dimensional continua, so we will continue with that. So, what we did in the previous lecture was we considered a triangular element. So, this element has 3 nodes 1, 2, 3, and at each node there are 2 degrees of freedom. So, this is a 3 noded element with 6 degrees of freedom. So, the field variables are u and v, which are functions of x, y and t, and we interpolate the field variable in terms of the nodal values. That means u is interpolated in terms of u1, u2, u3, and v is interpolated in terms of v1, v2, v3, and the interpolation functions are derived. So, that for example, the interpolation function n1 at this node will have value 1, and at these 2 nodes it will have value 0, and in this particular case we use linear interpolation functions. We also discussed rectangular plane stress element. Again the field variables here are u and v. This element has 4 nodes 1, 2, 3, 4, and at each node there are 2 degrees of freedom. Therefore, it is a 4 noded element with 8 degrees of freedom. Now, to facilitate the development of the element, we made a coordinate transformation. So, if you recall, the elements of stiffness and mass matrices for the element have to be evaluated by carrying out these integrations. This is stiffness and this is stiffness matrix, this is the mass matrix. So, to facilitate this integration, we transform this rectangular region to a square region, so that integration can be done from -1 to +1. Now, in the examples that we have considered so far, it has been possible for us to evaluate these integrals in closed form, but this may not be always possible. For example, if you have a quadrilateral element or a triangular element with curved edges, or a quadrilateral element with curved edges like this, evaluation of these integrals will not be straightforward. So, it becomes necessary to deal with 2 complexities. One is the complexity associated with the geometry and the complexity associated with evaluation of these integrals. So, these 2 issues we will try to take a look in today's class. So, we will consider, to start with, a linear quadrilateral element. So, this has 4 nodes. This is the coordinate system u and v, x and y, and u and v are the displacement fields. U is along x and v is along y, and this is the quadrilateral element with nodes 1, 2, 3, 4, and the nodal coordinates are x1, y1, x2, y2, x3, y3 and x4, y4. Now, we need to now approximate the field variable u and v, variables u and v within this domain. Now, what we do is we introduce a transformation so that a point in x, y here gets mapped to a new set of coordinates xi and eta that we have to introduce now, what these are, and this coordinate transformation is implemented exclusively for the purpose of evaluating these integrals. We will see what transpires when we implement this transformation. The main idea is to introduce this transformation to facilitate evaluation of the integrals. The stiffness matrix is given by this and the mass matrix is given by this. Now, the transformation that we are doing is from x, y is taken to psi eta. Therefore, we can consider the transformation in the mathematical form as x is a function of xi and eta, y is a function of xi and eta. Now, following the way we represent the field variables, we write now for this x and y this expression, where what we are doing is x of psi comma eta is being evaluated in terms of its nodal values and interpolation functions. Similarly, y is interpolated in the similar manner. So, what we are going to do is we are going to use the same interpolation functions that we used for representing the field variables to represent the geometry also. that is geometry of this transformation. Now, if you recall the n1, n2, n3, n4 for this configuration, we have arrived, we have shown that this is of this form, and compactly for all the 4 indices 1, 2, 3, 4 we have obtained this in the previous lecture. So, we will use this now here. Now, let us consider the line 2, 3 and this line 2, 3. Now, we want to investigate what is the relationship between the two. So, let us consider the line connecting x2 y2 to x3 y3. Upon making the transformation x equal to psi comma eta and y equal to y of psi comma eta, how does this line gets mapped? Or alternatively we can ask, if this is the transformation we are using, what happens to this line 2, 3 in this configuration? Whichever way you look at, we will find the answer to the required question. Now, let us therefore consider the line xi equal to 1 connecting 1 minus 1 and 1 comma 1, that means xi equal to 1, this line. Now, xi at the one of the vertices the coordinates are 1 comma minus 1. So, what happens to x there? X is x1 into n1 plus x2 into n2 x3 x4. Now, how does these shape functions behave? Except this n2, all other shape functions will be 0. So, this becomes x2. Similarly, you can write the value of y xi comma eta, that means where does this vertex 1 comma minus 1 in this coordinate system go in the original coordinate system. So, x has gone to, I mean this okay, let us see, x2 we have found out. Similarly, y will go to y2, that means if I am considering 1 minus 1, that means the second point here, it is going to 2 here. Similarly, the other vertex 1 comma 1, you can verify that this goes to x3 comma y3. Now, between these 2 points, does the variation remain linear or not? That is the next question we have to see. Now, consider the line xi equal to 1, which is that line? This line xi equal to 1. Now, x of psi comma eta is x1 n1 eta, and wherever xi is 1, xi is there, I will write it as 1. So, I get this expression. Okay, I am simply putting for xi 1. Then I will use the properties of these functions, and I will be able to show that this is given by this expression. It is a linear function of eta. Similarly, the y coordinate also get mapped to another linear function of eta, and I get x and y to be this. Now, I can eliminate eta from this and get the equation in xy plane what it is. So, if you do that, I get y minus this equal to this minus this. So, what I am doing is this I am taking to the left side, this to the left side and dividing, this 1 plus eta gets cancelled, this is what I get. Now, this is actually the equation of straight line passing through x2 y2 and x3 y3. So, we conclude that line 2 3 in figure A is transformed to line 2 3 in figure B. That means 2 3 is mapped to 2 3 here. So, we can summarize this. This is the line 2 3 which comes here, psi equal to 1. Psi equal to 1 is this line that comes here. Eta equal to 1 is this line, it comes here. Psi equal to minus 1 is this line, it comes here, and 1 2 is eta equal to minus 1, that comes here. So, that means that this quadrilateral is getting mapped to this through the transformation that we are proposing. So, these transformations of coordinates, that is x psi comma eta in terms of n and nodal values of x and nodal values of y for y, this is quite similar to the transformation on field variable. This is what I have been pointing out. This is the field variable, uj of t are the nodal values which are the degrees of freedom in our finite element model. That is, what we conclude from this is the same interpolation functions, these nj's, are being used to represent both the field variables as well as the geometric variables. The displacement field and the geometry of the element are getting represented through the same set of interpolation functions. The resulting element formulation is called isoparametric formulation. Okay, fine. So, what we have achieved is we have mapped a quadrilateral to a square. So, when we are performing integration, instead of performing over a quadrilateral which can be quite unwieldy, we have now the neat situation of being able to integrate over a square region. But what about the integrand? How does that behave? So, let us consider the evaluation of the mass and stiffness matrices by transforming xy to psi comma eta coordinates. This transformation we will now implement. So, we need to digress a bit now to understand what the problem is. So, first is we will consider a function f of x y in Cartesian coordinates, and using this transformation xi eta, if we map x and y to xi and eta, what is the rule of transformation? See, this is the rule as you may be knowing, but how does it really originate? To be able to do that, let us consider a point, this point with a position vector r in xy plane. So, that is r is ix plus jy. Now, psi and x are functions, psi and eta are functions of x and y. So, now I want that is this is a psi and this is a eta, some coordinates. Okay. So, now I want to deal with this situation. So, what is dou r by dou psi? It is I dou x by dou psi plus j dou y by dou psi, where I and j, I, j, k are unit vectors along x, y and z respectively. Similarly, dou r by dou eta is I dou x by dou eta plus j dou y by dou eta. AB, the line AB if you see is, what is this? So, this plus this is equal to this is a vector sum. So, if you are looking at AB, it is simply the difference between the two, which is this dou r by dou psi into d psi. Similarly, if you look AD, it is the vector difference of this and this, position vector of D and position vector of A, and that AD is this. Now, the area element dA is given by the triple product of these two position vectors and the k along this gives the area. This is a result from vector algebra. So, you can recall that, and if we do that and now put substitute for dou r by dou psi and dou r by dou eta, the quantities that we have just now derived, and this itself can be expressed as a determinant. See, we have shown just here dou r by dou psi and dou r by dou eta, and this is what I am substituting here, and implement this cross product. You should know the rule of cross product and the dot product. So, if you do that, you get this expression. Now, this quantity inside this parenthesis can be written as a determinant, and the matrix associated with this is the Jacobian matrix, and this is the determinant of the Jacobian. So, dA is therefore Jacobian of the transformation into d psi d eta. Therefore, I is integral f of x y dx dy A becomes now -1 to +1 this. Now, that is one first part of our digression. The second is the question of numerical integration. So, you may be familiar with trapezoidal rule, Simpson rule and Newton-Cotes formula, etc. But we will consider what are known as Gauss quadrature rules, and I will explain what the rationale of those rules are. So, let us consider for sake of discussion an evaluation of an integral I cap a to b f of x dx. First, let us transform x into a new variable u, so that the limits of integration are from -half to +half. So, what I will do? I will substitute u as alpha x plus beta. Alpha and beta are the two parameters which I do not know. So, when we are at the lower limits, I want this to be -half. So, I want u to be -half when x is a, and u to be +half when x is b. So, that helps us to solve for alpha and beta, and the transformation I am looking for is given by this. So, if you substitute that into this equation, I will get -half to +half f of this u now b minus a du. So, this is equal to b minus a into I, where I is this integral. So, I call this f of b minus a u plus a plus b by 2 as phi of u du. So, we will focus our attention on discussing how to evaluate this integral. So, now what I wish to do is, I have this function phi of u and this is my u axis from minus half to plus half. I want to evaluate this function at some sets of points u1 u2 some un, and I want to attach a weight r1 to phi of u1, r2 to phi of u2 and be able to evaluate this integral. So, I am looking for evaluation of I by using this representation. So, the effort here will be spent in evaluating phi of u. So, any integration method that we use, if we should get the ideal integration scheme, is get a good approximation for I with minimum number of evaluation of phi of u, or in other words, if you evaluate say phi at say 10 points, which is the best way that I can combine them, right. For any other combination, you can use trapezoidal rule and things like that, then you can evaluate R, but then you are constraining yourself to place ui's in a particular manner. So, the weighting factor also can be optimized. Now, the question is therefore how to select n, that means how many number of points, how to select these weights and where to place these points where I am going to evaluate these functions, so that I get a good approximation to I. Keeping this ui plus 1 minus ui as a constant, that means you sample it at a constant step size, that may not be the ideal situation, because that depends on how this function varies. Okay. It may not lead to the best solution always. Now, assuming that phi of u is continuous between minus half and half, we write now a power series expansion, convergent power series expansion in this form. So, in this form. Now, this minus half to plus of phi of u du, now for phi of u I substitute this summation, assumed summation, which is this 0 to infinity am um du, and upon performing integral I get this. So, I can evaluate these terms, and in terms of the unknowns a naught, a1, a2 etc., I can get an expansion like this for the integral. Now, so this is the expansion we have got. Now, we have this power series representation for phi of u. Now, if I evaluate phi of u at ui, this will be the representation. Okay. Now, therefore, now I will substitute this into the representation that we are using. So, phi of u du is approximately this is what is our proposition, and for phi of ui I will write this expansion, this is what I get. So, I get now a representation, I will interchange the order of summation and I will get a summation representation like this. So, in longhand, if you expand this R1 into this infinite number of terms, R2 into infinite number of terms, so on and so forth. Now, this I know right hand side what it is, and the left hand side I have I am rearranging the terms now. A naught I will collect, coefficient of a naught are collected, that is R1 plus R2 plus Rn, A1 is this, Am is this, and this continues. Now, I will now compare the coefficients of a naught, a1, a2, a3 on both sides, I will get a set of equations now. For this to be equal, coefficient of a naught here is 1 and coefficient of a naught here is this should be satisfied. And similarly, coefficient of this is a naught, a1, there is 0 here, so that must be 0. So, by writing this we can write as many equations as you want. Suppose if you consider 2n equation, there will be 2n unknowns. What are the 2n unknowns? R1, R2, Rn first set, then u1, u2, un, 2. So, that constitute 2n unknowns. Now, you select these 2n equations and solve for those 2n unknowns, and that gives you the representation that you are looking for. But how do you solve for that? This is a set of nonlinear equations. you can see quadratic terms here. So, they are nonlinear equations, but there is a nice result which shows that if phi of u is a polynomial of degree not higher than 2n minus 1, then these u1, u2, un, which are the points where I want to evaluate the function according to the prescription that I just outlined, would turn out to be the zeros of Legendre polynomials Pn of u. That means these u's will satisfy this equation. So, the roots and these roots are real. So, once these roots are determined, if I know u1, u2, un, then the remaining n unknowns which are r1, r2, rn can be solved by solving a linear problem. Is it okay? So, I can find this constants as I wish. So, if you are dealing with a polynomial, then if you retain adequate number of terms, you will be evaluating the integral exactly. There is no approximation at all. Okay. Now, for example, n equal to 3, we have this is the rule according to which we want to evaluate. So, if you expand this now for n equal to 3 and carry out this differentiation, I get this equation. So, it turns out that the roots of the equations are u equal to 0 and plus minus half square root 3 by 5. So, the first point I have to select is this, second one is 0, third point is this. With these weights if I add and evaluate the integral. So, 2n minus 1 means 4, 6 minus 1, a fifth order polynomial will be exactly evaluated by these weights, okay, because the function is polynomial. Now, I have done a few calculations here for different values of n, the roots, these are the roots of the Legendre polynomial. This is for n equal to 1, 2, 3, 4 and these are the weights. Okay. So, if you are implementing this, you can use this information to do this. Now, we can see how these formula perform. Now, if I want to evaluate integral minus 1 to plus 1, the answer is 2. So, if I take one term, it gives the exact answer. So, the rule is a polynomial of order p is integrated exactly by employing n number of terms, which is smallest integer greater than 0.5 p plus 1. So, now x, so 1, so p plus 1 is 2, you need at least one term. If you use one term, you will get exact solution, but this is of course 0 because it is a odd function under symmetric limits, there is no problem. But you come here p equal to 2. So, 2 plus 1 is 3, 1.5, I need at least 2 terms before I can get the value of the integral correctly. So, if you see here, if I take only 1 point, I get answer as 0, which is wrong. If I get 2 points, this is the exact answer, x cube by the whatever, you can quickly do this, we get for n equal to the right answer. Similarly, 3 of course there is no problem, 4, this is 4 plus 1, 2.5, I should have at least 3 terms. So, with 0, 1 term I get 0, 2 terms I get 0.22 and this is 0.4. Now, 6 plus 1, 7, 3.5, I would need at least 4 terms to get that. So, 0.2857 is the exact answer, 1 does not give a good answer, 2 is this answer, 3 is this, 4 gives the exact answer. So, you can quickly verify these things, the information needed to check this table are here. Now, what we now will return to the evaluation of the integrals. This is a mass matrix and as using the first result I will be able to write in this form, okay, upon transformation, that is our first set of results that we got. Now, how do we evaluate this integral is a question. Now, we propose to evaluate this integral using Gauss quadrature. So, for that to do that correctly, I should know the order of the function which is this integrand. That means, how does n transpose n into determinant of j vary with respect to eta and xi. If I know that, then I will be able to select the correctly the number of integration points. Otherwise, I will again, as you saw here, if your integrand is x to the power of 6 and if you happen to take n equal to 3, you will not get a right answer, you have to take n equal to 4. Because you know this rule, you will be able to make this choice. Now, we have to now work through the evaluation of this determinant of the Jacobian. So, what we know right now, Jacobian is given by this Jacobian of the transformation, x we are writing like this and y we are writing like this. So, given this I can now substitute for these derivatives in terms of nj's, and using this expression I will be able to write J as product of two matrices. The first matrix contains derivatives of n1 and n2 with respect to xi and eta, and second matrix contains the coordinates of the nodes. Okay. So, all these quantities are known. So, we can go ahead and perform the calculation. If you can it is quite straightforward to do this. If you do this, I get J to be in this form where E1, E2, F1, F2 and F3 are explained here in terms of nodal coordinates. So, moment I have this, I can evaluate the determinant of J and it turns out to be this, and interestingly it turns out that the determinant of J in this case is a linear function of xi and eta. It is precisely this that I wish to determine, then only I will know which order of integration I need to implement. We knew the order of n transpose n because we know entries in n, so we know what order that product would be, but we did not know what was the order of this J is. I mean we did not even know whether it is linear or not first of all. So, if we now look into this, we see that it is a biquadratic or a bicubic function depending on which terms you are looking at. So, using the rule that we are using, a 2 by 2 array of integration points would be adequate to perform this integration. So, mass matrix can be evaluated exactly by using Gauss quadrature with 2 by 2 Gauss quadrature point mesh. How about stiffness matrix? So, I need here B transpose dB into the Jacobian. So, again I need to perform some calculations here. So, this D matrix has to operate now. So, I need this information, dou by dou psi is dou x by dou psi into dou by dou x plus dou y by dou psi into dou by dou y, etc. And this if we put in the matrix form, I have this vector of gradient dou by dou psi and dou by dou eta, and this is the Jacobian matrix this. So, I can either write this or the inverse of this, I can express dou by dou x and dou by dou y in terms of dou by dou psi and dou by dou eta through J inverse. Now, B, recall B was this for this problem. So, we get after multiplication I get this, and it turns out that the quantity that we are looking for is given in this form. Okay. So, elements of B transpose dB into determinant of J are ratios of biquadratic functions and linear functions. See, there is an inverse here. So, there is therefore, if you look at individual terms, they will not be polynomials, they will be ratios of polynomials. Okay. It turns out they are ratios of biquadratic functions and linear functions. So, this would mean Gauss quadrature will not be able to evaluate elements of Ke in an exact manner. So, if you use Gauss quadrature to evaluate this, we are introducing certain approximation, but Gauss quadrature is so convenient, we will make some discussion on this subsequently, but right now the recommendation based on experience is use a 2 by 2 Gauss quadrature. We will come to this slightly later once again. Okay. So, summary is mass matrix gets evaluated exactly, and stiffness matrix there will be an approximation. Now, this is I have used now a 4 noded quadratic element. Now, the question is, if you are using discretization, if you are modeling any structural behavior, how do you improve upon the accuracy? One way is stick to 4 noded quadrilateral elements and use more of them, that means refine the mesh, introduce more number of elements and do that. The other way is use a higher order polynomial to interpolate the field variables. If you want to do that, it amounts to increasing the number of nodes in an element. So, instead of having 4 noded element, we can have 8 noded element. Okay. So, then when I interpolate, the interpolation functions will be of the higher order polynomials, they will not be what we saw for a 4 noded element, because now there are additional nodes that come into our formulation. Suppose I take this I will, as before, I will retain these 3 nodes and introduce additional nodes at the midpoint of each of these elements. Again we will transform this to a square region and evaluate the elements of stiffness and mass matrices using Gauss quadrature. So, this is a 8 noded quadrilateral element with 16 degrees of freedom. Now, the field variable now needs to be represented in terms of the nodal values, and there are 8 nodal values for u. So, if you go back here for a u1, u2, u3, u4, u5, u6, u7, u8. So, I have to utilize all of that to interpolate u of x comma y comma t to facilitate the development of this element. Now, similarly V is represented like this. Now, using the logic that we have already discussed, we need not have to go into all the details every time. For we get these interpolation functions which have this Kronecker delta property. For nodes 1 to 4 I get this is the interpolation function, for 5 and 7 these are the interpolation functions, and 6 and 8 we get this. Now, I would not like to get into all the details of the formulation of these integrands, but if you indeed perform all that, you will be able to notice that you need to use 3 by 3 Gauss integration points. With a 3 by 3 mesh, mass matrix is evaluated exactly, but the stiffness matrix continues to be evaluated approximately. Now, how about this is a rectangular element. This discussion is not for this element, this is for this discussion is for a rectangular element. For a quadrilateral element the same formulary works, except now that the x and y also need to be interpolated using the same shape functions. Okay. So, in this case it turns out we need to use 4 by 4 Gauss integration points in evaluating stiffness and mass matrices, and if you use 4 by 4 mesh, the mass matrix is evaluated exactly. So, the mesh size that you need to select should be such that the mass matrix elements of mass matrix are evaluated exactly. See, mass matrix elements turn out to be polynomials because n transpose n remains as polynomial, whereas here because of the Jacobian also of course would play a role, but here because of this various operations involved here, the K matrix there will be difficulties as we saw a while before. Now, let us return to the shear wall and earth dam example that we considered in the previous lecture. So, the problem was there is a shear wall of thickness 0.2286 meters, and these are the dimensions, and the problem was to find first 5 natural frequencies and normal modes. Now, analytical estimates of natural frequencies using Timoshenko beam theory were obtained, were pointed out. These were the numbers, these are frequencies in hertz. Now, we discussed this model in the previous lecture. We used 64 elements with first order elements, that means we used 4 noded quadrilateral elements, actually they were rectangular elements here, and the degrees of freedom that the model had was 160. Now, what I have done is we have retained the same mesh and same element configuration, but now the elements are modified to be second order elements, that means they are now 8 noded quadrilateral elements. So, the degree of freedom increases to now 448, and the natural frequencies from 5.03 I come to 4.95, and these numbers change, and you can see here they are reasonable if this is believed to be correct because it is an analytical solution and the structure structural geometry satisfies the requirements for the application of Timoshenko beam theory. So, consequently we can trust this result. And this is analytically derived. So, we see that the first natural frequency is much better approximated than this. Similarly, the other frequencies also get represented better. So, these are the mode shapes, first 4 mode shapes are shown here. So, you can see that now the mode shapes are smoother because they are represented with greater detail within an element. This is the 10th mode. Higher modes become a representation of higher modes would not be so smooth as it is seen here. If we had used the first order element, this mode would not be as smooth as is seen here. Now, this earth dam problem, it was a triangular wedge modeled using plane strain approximation, and these were the properties: Poisson's ratio 0.45, this is the density, and this is the Young's modulus. With triangular elements, with 42 elements and 42 degrees of freedom, we got these natural frequencies. And if you use a shear beam model, and this is analytical estimate of the shear beam natural frequency, this is available in terms of Bessel's functions, then exact solution to this is available. So, based on that, these numbers have been computed. Now, this we have done in the last class. Now, what I have done now is this analysis is with first order triangular elements. Now, this analysis is with second order triangular. Although I did not discuss the formulation of second order quadrilateral element, the logic is conceptually quite similar to what we briefly mentioned for quadrilateral elements. So, if I use this same number of elements, but the order has increased, so degrees of freedom will increase. So, the frequencies now change, and the first frequency is, if we have to believe this is 1.25, this is 1.227, and this seems to be moving towards that. But mind you, this is also an approximation to this behavior of this wedge. So, the underlying assumptions of shear beam behavior must be satisfied by this structure. So, it is difficult to pass a clear judgment on which of these two are exact. Now, these are the mode shapes from a higher order element. This is first mode and fifth mode. This matches with what we did with the coarser element, I mean first order element. Now, in this illustration, I am using a combination of triangle and quadrilateral elements. This is quadrilateral element, this here we are using triangular elements. So, this is again first order elements. So, there are 32 elements, 56 degrees of freedom, and we get natural frequencies like this. So, this is just for illustration, and these are the mode shapes that we obtain from this model. Now, what I do, I will repeat this exercise using the same mesh. Instead of first order element, I will use second order element. So, this quadrilateral element here has 8 nodes and 8 degrees of freedom. The triangular elements here will have 6 nodes and 12 degrees of freedom. So, number of elements remain the same, there are 210 degrees of freedom, and I get different sets of estimates for natural frequency. So, these are the mode shapes for the two first and the fifth mode. Now, so far what we have discussed is basically free vibration problems. Now, if we have to consider forced vibration response, we need to worry about how the equivalent forces are computed. So, let me just the basic rule for that is this. Okay. So, to explain this, what we will do is we will consider a suppose there is a edge 2 3 in a triangular element, and this is the loads will be in the plane of the element, it is a plane stress problem. Suppose at any point here there is a load Px and load this load Py. Now, when we formulate the finite element model, we also need to assemble the nodal forces. First of all, we should evaluate the equivalent nodal forces. So, what we do is we have this over the surface of the element d delta u delta v transpose Px Py into ds. Now, we also have the approximation uv which is n into uv. So, now we write delta we for the nodal in terms of the equivalent nodal forces. These are the forces that are acting on the surface. I want to represent them in terms of equivalent nodal forces. So, we demand that equivalence of these two will give me the expression Fe equal to see I have to consider the edge 2 3. I am assuming if you saw recall we are considering force on the edge 2 3. So, this has to be evaluated along that edge. So, if I do this we will get Fe for the example that we have considered as half length of 2 3 into 0 0 0 Px Py Px Py transpose. So, what we are getting is at the two nodes half of the load comes here, half of the load goes there as per this formulation. So, this is what the equivalent nodal forces, the logic for computing equivalent nodal forces. This can be done for quadrilateral elements and rectangular and quadrilateral elements as well. So, at some point we will illustrate this with some examples. Now, in the subsequent lectures what we will do now, so far what we have done is we have dealt with a 3D beam element with 2 nodes and 6 DOF per node. Now, we have now considered 2D continuum, we have derived different elements. Now, the generalization for further analysis, now there are 3 things that we can do. This beam theory will be get extended to plate and shell. This 2D continuum we can consider now 3 dimensional problems. That means, when conditions of plane stress and plane strain are not satisfied, here another 2D model becomes possible, that is axis symmetric solids and then 3D solids. So, what in the remaining next few lectures what we will do is we will develop the structural matrices for these problems and these problems, and at the end of it I will, at the end of these developments I will make a few remarks on choice of shape functions and their role on how the answers converge. Now, we will consider the question of how to compute equivalent nodal forces. We will quickly recall what we did for a beam element. So, this is a beam element say 2 dimensional beam element deforming in its own plane. This is the distributed load f of x comma t. So, discretization of this element, we had 2 nodes and 2 degrees of freedom per node u1, u2, u3, u4 were the 4 degrees of freedom for the element. The problem here is, see, the displacement field is represented in terms of nodal displacement and these interpolation functions. So, how do we represent this distributed load in terms of equivalent nodal forces? So, how to find P1, P2, P3, P4 in a way that these form an equivalent, there is an equivalence between this load and this set of loads. So, what we considered was a virtual displacement and that we represented in terms of virtual nodal displacements multiplied by the interpolation functions, and the work done was equated. So, the work done by virtual displacements on this set of forces and the virtual displacement on this by this set of forces are equated, and by manipulating the terms we determined the nodal forces to be given by these expressions. So, we are going to do something similar for even 2 dimensional elements. So, suppose Px and Py are the distributed loads along the edge 2, 3. Now, I want to find out what is the equivalent nodal forces because of these forces. So, Px and Py are distributed along this edge 2, 3. So, the virtual work is given by this expression, and the displacement field we are interpolating in terms of nodal degrees of freedom as shown here. Now, along this edge, so this virtual work can be written in terms of virtual displacement and applied forces as shown here, and this is our representation. So, the virtual work which is this is also equal to virtual nodal displacements into these forces, and after we manipulate this we get this expression, and we should note that this trial functions need to, here we need to be evaluate this along the edge 2, 3. Now, this is the virtual nodal displacements into the nodal forces, and by equating these two we get the by equating this and this we get the expression for equivalent nodal forces which is shown here. Now, here we have assumed that Px and Py are constant along the edge, otherwise there will be a quadrature that has to be implemented. The subscript L2, the quantity L23 represent length of the edge 2, 3, this length. So, if you know the nodal coordinates, you can derive that length in a straightforward manner. Now, we can make some remarks. First is the quadrature rule that we discussed was in the context of a scalar integral. This can be, the same formulation can also be extended to 2 dimensional integrals, and one gets quadrature rule of this form. Now, in this calculation of equivalent nodal forces, we considered surface tractions, but if there are equivalent there are body forces within the element, we can denote them by Fx Fy transpose. Suppose if that body force is constant within the element, how we can find the equivalent nodal forces? That again we have to use the same formulation. I leave this as an exercise. This will be the equivalent nodal forces, and here again we need to evaluate this integral, and we need to examine the order of terms in the integrand and decide upon the quadrature rule, but this needs to be evaluated again using Gauss quadrature. Now, a small exercise. So, let us consider a 4 noded linear rectangular element. Now, we consider the displacements in the discussion so far we considered this part. Now, to this I will now add 2 more terms, alpha 1 1 minus xi square, alpha 2 1 minus eta square, and similarly for v I will add this. Now, you can see here that at the nodes which are xi equal to plus minus 1 and eta equal to plus minus 1, these terms are 0. So, this is like a bubble function. So, they do not affect the behavior of u near the nodes, at the nodes, and v is given by this similarly. So, now again these trial functions are same as what we have used for a linear rectangular element. Now, these alpha 1, alpha 2 and alpha 3, alpha 4 are not nodal displacements now, they are generalized coordinates. So, there will be now 12 degrees of freedom for the element, 4 nodal displacement u1, u2, u3, u4 and 2 generalized coordinates alpha 1 and alpha 2. Similar, this is 6 for u, similar 6 quantities for v. Now, the exercise that that is being suggested is use the energy expressions and obtain the 12 by 12 stiffness matrix and eliminate these alpha 1, 2, 3, 4 in terms of the nodal degrees of freedom using static condensation and obtain a 8 by 8 stiffness matrix. And also examine are the displacement fields continuous across the element boundaries. So, this exercise can be carried out. So, in using this element you may notice that we can continue to use the consistent mass matrix that was derived using only this approximation. Kinetic energy can be characterized using only this, and whereas the displacement fields will be the kinetic strain energy will be computed by an alternative representation. Now, in the subsequent lectures now, we will now consider problems of 3 dimensional elasticity. We have briefly discussed this earlier, so we will quickly recall. So, stress state of stress is now described in terms of 6 stress components, either it can be arranged as a matrix or a vector like this. These are the strain components, and for an isotropic linearly elastic material the stress and strain are related through this relation, and this is the matrix D, and we have the expression for strain energy and kinetic energy. This is sigma transpose epsilon dV naught is the expression integral of that over volume element into half is the strain energy, and this is the kinetic energy. Now, to compute strain energy we can now what we are doing is we are expressing sigma in terms of strain, and the strain subsequently we will express in terms of displacement as we have been doing. This is a strain displacement relation for small deformations, and substituting that we will get displacements as n into ue, where ue are the nodal displacements, and consequently epsilon is obtained in this form where B is equal to this matrix into n. So, given that we will have the expression for strain energy and kinetic energy in terms of assumed displacement fields as given here, and we need to now carry out this integration over the volume elements. Now, the volume elements in a 3 dimensional solid becomes more diverse. We can have a tetrahedron or a rectangular hexahedron or a pentahedron or an isoparametric hexahedron, and we can also have isoparametric versions of tetrahedron and pentahedron, and these can be first order elements or higher order elements. So, there is a great diversity of elements. So, we can examine some of them as we go along. Subsequently, in 3 dimensional problems we can also consider solids of revolution. These are called axisymmetric problems. We will be doing that, and we will develop at least one element for this type of applications, and this would be followed by a discussion on a plate bending element. So, this is a thin say lamina which carries now transverse loads in addition to the inline loads. So, the action of these transverse loads on this lamina is to the plate is to induce bending and about x and y axis, and we need to formulate the correct expressions for strain energy and kinetic energy and develop the elements. So, we will take up these exercises in the following lectures, and maybe some examples on forced response analysis. So, with this we will conclude this today's lecture.